Langchain upstage chat models. Fine-tuned versions of large language models that are optimized for specific tasks. These models are trained on domain-specific datasets to perform specialized tasks, like summarizing legal documents, writing creative content, or translating languages. Inputs. Input text: the text that the model will process and generate output from. This could be a paragraph, an article, or a question. Task-specific instructions: instructions that guide the model on how to process the input text and generate the desired output. For example, you might instruct the model to summarize the input text in 50 words, translate it into Spanish, or answer a specific question from the text. Outputs. Text output: the output generated by the model based on the input text and task-specific instructions. This could be a summary, a translation, a creative writing piece, or an answer to a question. Task-specific results: results that are specific to the task being performed. For example, if the task is to summarize a document, the task-specific result could be the number of words in the summary or the length of the summary in terms of characters. If the task is to translate a document, the task-specific result could be the language into which the document was translated. Steps. Define a task or domain-specific dataset. The first step in fine-tuning a large language model is to define the task or domain for which the model will be trained. This involves identifying the specific type of text that the model will process, the desired output, and the criteria for evaluating the model's performance. For example, if you want to fine-tune a model for summarizing legal documents, you would need to define a dataset of legal documents and identify the key features of a good summary, such as accuracy, conciseness, and clarity. Train a large language model using the dataset. Once you have defined the task or domain-specific dataset, you can train a large language model using the data. This involves feeding the model the dataset and allowing it to learn the patterns and relationships within the data. The goal is to train the model to generate outputs that are consistent with the task or domain-specific requirements. Prerequisites. Upstage account: a free or paid account with Upstage, a platform for fine-tuning large language models. This account is required to access the platform's tools and resources for training and deploying fine-tuned models. Upstage application programming interface key: an API key provided by Upstage that grants access to the platform's API. This key is used to authenticate your requests to the API and authorize you to perform specific actions, such as uploading data, training models, and deploying models. Relevant dataset: a dataset that is relevant to the task or domain for which you are fine-tuning the model. This dataset should include a large number of examples that are representative of the type of text that the model will process. For example, if you are fine-tuning a model for summarizing legal documents, your dataset should include a large number of legal documents. Task-specific dataset: a dataset that is tailored to the specific task for which you are fine-tuning the model. For example, if you are fine-tuning a model for summarizing legal documents, your task-specific dataset could include legal documents that are annotated with their corresponding summaries. Fine-tune parameters. Learning rate: a parameter that controls how quickly the model learns during the training process. A higher learning rate means that the model will learn more quickly, but it also increases the risk of overfitting. A lower learning rate means that the model will learn more slowly, but it will be less likely to overfit. Batch size: a parameter that controls the number of examples that are processed in each step of the training process. A larger batch size means that the model will learn from more examples at each step. But it will also take longer to complete the training process. A smaller batch size means that the model will learn from fewer examples at each step. But it will complete the training process more quickly. Challenges and fixes. Data quality issues. Data quality issues can significantly impact the performance of fine-tuned models. For example, if your dataset contains errors, inconsistencies, or duplicates, the model may learn incorrect patterns or relationships, leading to poor performance. Clean and pre-process the dataset before training a model. It is essential to clean and pre-process the dataset to address data quality issues. This involves removing errors, inconsistencies, and duplicates, as well as performing other pre-processing steps such as tokenization, stemming, and normalization. Overfitting to specific examples. Overfitting occurs when the model learns the training data too well and fails to generalize to new data. This can happen when the model is too complex or when the training data is too small. Use regularization techniques. Regularization techniques help to prevent overfitting by penalizing complex models. These techniques can include L1 and L2, regularization, dropout, and early stopping. Long training times. Fine-tuning large language models can be time-consuming, especially when using large datasets. Use distributed training methods. Distributed training methods allow you to train models on multiple machines simultaneously, which can significantly reduce training time. These methods involve splitting the data and model across multiple machines and then training them in parallel. Langchain together. Chat models. Chat together. Chat together is a langchain component that enables collaboration among multiple large language model LLM agents to accomplish a single task. Inputs. A collection of LLM agents, each distinguished by its unique capabilities and knowledge base. For example, one agent could be specialized in summarizing text, while another excels in code generation. A specific task or question demanding diverse perspectives or expertise for an effective resolution. Imagine, for instance, analyzing a complex research paper by combining the insights of agents skilled in scientific literature review and factual accuracy. Outputs. A unified response that integrates the contributions and insights of all participating LLM agents. This consolidated output delivers a more comprehensive and well-rounded answer than any individual agent could achieve on its own. Steps. Initiate the chat together object by providing a list of LLM agents and the task to be executed. The chat together object systematically interacts with each LLM agent, presenting them with the task and any relevant contextual information. Each LLM agent processes the task using its unique capabilities and generates a response based on its understanding. The responses generated by all agents are subsequently merged into a unified, coherent output. This final output incorporates the diverse perspectives and insights of each participating agent. Prerequisites. Install the necessary Python libraries, including langchain, OpenAI, and Hugging Face transformers. These libraries provide the foundational tools for working with and managing LLMs in your Python environment. Obtain application programming interface API keys for the desired LLM models, such as GPT-3 or Bloom. API keys authenticate your access to these powerful language models and enable you to integrate them into your applications. Fine-tune parameters. The number of LLM agents to participate in the collaboration. Experiment with different numbers of agents to optimize the complexity and diversity of Perspectives brought to bear on the task. The specific LLM models to employ for each agent. Consider leveraging agents with complementary strengths, such as a factual model and a creative model, to achieve a more balanced and informative result. The communication protocol for agent interaction. Choose a communication protocol that facilitates clear and efficient information exchange among agents. For instance, a message passing protocol might define structured messages to ensure that agents understand each other's intentions and responses. Challenges and fixes. Challenge 1. Managing communication and coordination among multiple LLM agents. This involves ensuring clear and efficient information exchange, particularly when dealing with complex tasks requiring multiple perspectives and capabilities. Fixes to Challenge 1. Employ structured communication protocols, such as message passing with specific formats. This enables agents to convey their ideas and responses in a standardized way, minimizing ambiguity and promoting efficient information flow within the group. Challenge 2. Ensuring consistency and coherence in the final response from multiple LLM agents. This challenge arises from the inherent diversity of agent perspectives and potential inconsistencies in their responses. Fixes to Challenge 2. Utilize a central aggregation mechanism that combines and harmonizes the outputs from individual agents. This mechanism analyzes the responses, identifies potential conflicts, and synthesizes them into a cohesive and consistent final output. Challenge 3. Preventing redundant or irrelevant contributions from LLM agents. This challenge stems from the possibility that agents may provide overlapping or irrelevant information, leading to a less efficient and focused output. Fixes to Challenge 3. Implement mechanisms to filter or prioritize agent responses based on their relevance and novelty. This ensures that the final output prioritizes valuable and unique insights, minimizing redundancy and maximizing overall output quality. Langchain Upstage Chat Models. Chat Upstage Summary. A large language model that enables users to generate chatbots. It uses a transformer-based architecture trained on a massive dataset of text and code. This model is capable of understanding and responding to user input in a way that mimics human conversation, making it ideal for creating chatbots that can provide information, answer questions, or engage in casual conversations. Inputs. Text input to be processed. This refers to the textual data that the model uses to learn and understand the context of a conversation. For example, a user might provide a description of the topic the chatbot should be able to discuss, or a set of example conversations that the chatbot should be able to replicate. User preferences for chatbot style and tone. These preferences allow users to customize the personality and behavior of the chatbot. For example, a user might specify that they want a chatbot that is informative, humorous, or formal. Outputs. A chatbot that can engage in natural and informative conversations with users. The output of the model is a functioning chatbot that can interact with users in a conversational manner. This chatbot can be deployed in various applications, such as customer service, e-commerce, or education. Steps. The user provides the model with text input and chatbot preferences. The user begins the process by providing the model with the necessary information, such as the desired topic, conversation style, and any relevant examples. The model processes the input and generates a chatbot that can respond to user prompts. The model then utilizes this information to learn and generate a chatbot that can understand and respond to user input in a way that aligns with the provided preferences. Prerequisites. Upstage account. This refers to an account on the Upstage platform, which provides access to the necessary resources and tools for using the model. Upstage Application Programming Interface Key. This is a unique identifier that allows the user to access and interact with the Upstage platform and its services. Langchain library installed. The langchain library is a powerful tool that enables users to connect and orchestrate different language models, including the one used in this context. Langchain library initialized. This means that the langchain library has been set up and configured to work properly, allowing users to interact with it and utilize its functionalities. Fine-tune parameters. Model size. This refers to the number of parameters in the model, which influences its complexity and performance. A larger model generally has higher capacity but also requires more computational resources. Learning rate. This parameter controls how quickly the model adjusts its weights during training. A higher learning rate can lead to faster convergence but might also result in instability. Challenges and fixes. Chatbot responses may not be coherent or informative. This can happen if the model has not been trained on a sufficiently relevant dataset or if prompt engineering is not effective. Fine-tune the model on a relevant dataset or adjust the prompt engineering to improve coherence and informativeness. Users can fine-tune the model on a dataset that is specifically related to the desired topic or conversation style. They can also experiment with different prompt formats and instructions to guide the models. Responses. Chatbot may not be able to handle complex user requests. This can occur if the model lacks the necessary conversational logic or access to external knowledge sources. Implement more sophisticated conversational logic or integrate external knowledge sources. To address this challenge, users can implement more advanced conversational logic within the chatbot, allowing it to handle more intricate user requests. They can also integrate external knowledge sources, such as databases or APIs, to provide the chatbot with access to a wider range of information. Langchain Upstage Chat Models Summary. A tool for fine-tuning large language models using langchain to improve performance on specific tasks. For example, you might want to fine-tune a language model to be better at summarizing text or generating code. Langchain provides a framework for efficiently carrying out this process. Inputs. Training data relevant to the task to improve performance. For example, if you want to fine-tune a language model to write poems, you would provide a dataset of poems as training data. The base large language model to be fine-tuned. This is the model that will be used as the starting point for fine-tuning. Examples of large language models include GPT-3, Lambda, and BERT. Outputs. Fine-tuned language model that performs better on the specific task. The fine-tuned model will be better at the specific task you are aiming to improve. For instance, a model fine-tuned for writing poems will generate better quality poems compared to the base model. Steps. Define the specific task to be improved. This could be anything from summarizing text to translating languages. You need to be very specific about the task you want to improve. Prepare training data relevant to the task. This will be a dataset of examples that represent the task you want to improve. For example, if you want to improve the model's ability to summarize text, you would provide a dataset of text documents paired with their summaries. Fine-tune the base language model using the training data. This process adjusts the parameters of the base language model using the training data, resulting in a model better suited for the specific task. Think of this like training a dog. You need to give it the right examples and rewards to learn the desired behavior. Prerequisites. Access to a large language model that can be fine-tuned. This is a model that can be adapted to improve its performance on specific tasks. You will need to have access to the model's weights and the tools needed for fine-tuning. Relevant training data for the specific task. This is the key ingredient to fine-tuning a model. The training data should be directly relevant to the task you want to improve. And it should be high quality. Fine-tune parameters. Learning rate. The learning rate controls how much the model's parameters are adjusted during each training. Iteration. A higher learning rate will make the training process faster but might lead to instability. A lower learning rate will be slower but potentially more stable. You need to find the right balance. Batch size. The batch size controls how many training examples are used in each training iteration. A larger batch size will make the training process faster but might require more memory. A smaller batch size will be slower but might be more stable. Challenges and fixes. Overfitting to training data. Overfitting occurs when the model learns the training data too well and fails to generalize to new data. This is like a student memorizing the answers to exam questions but not understanding the underlying concepts. Use techniques like data augmentation and early stopping to avoid overfitting. Data augmentation expands the training data by adding variations to existing examples. Early stopping halts training before the model overfits to the training data. These techniques help the model generalize better to new data. Lack of data for fine-tuning. Fine-tuning requires a significant amount of data to achieve good performance. If you don't have enough data, it can be challenging to train a model that generalizes well. Utilize transfer learning by fine-tuning. On a related task with more data. Transfer learning involves using a model already trained on a related task. This can be helpful if you don't have a large amount of data for your specific task. For instance, if you want to fine-tune a model for writing poems, you could first fine-tune it on a larger dataset of text generation. This process would then serve as a good starting point for fine-tuning on a smaller dataset of poems. Langchain Upstage Chat Models. Chat Upstage Summary. Chat Upstage is a large language model LLM specialized in generating different types of outputs, particularly code. It can be used to translate natural language prompts into working code or text, making it a valuable tool for developers and writers. Inputs. Natural language prompt. This refers to the user's input in plain English, describing the desired output. For example, write a Python function to calculate the factorial of a number. Outputs. Code. Chat Upstage can generate code in various programming languages based on the prompt. It can create functions, scripts, or entire programs, making it useful for developers looking for quick solutions or exploring new coding concepts. Text beyond code. Chat Upstage can also produce text outputs. This might involve writing stories, generating summaries, translating languages, or even composing poems. The text output is based on the user's prompt and the model's understanding of language. Steps. Convert prompt to Chat Upstage format. The input prompt is processed and structured in a way that Chat Upstage can understand and interpret. This step might involve identifying keywords, recognizing the desired programming language, and converting the request into a format suitable for the model. Run Chat Upstage model. The formatted prompt is then passed to the Chat Upstage model. The model processes the prompt and generates an output based on its training data and the provided instructions. This step involves sophisticated algorithms and computations to produce the desired result. Format output. The output generated by the model is then formatted and presented to the user. This might involve structuring code with proper indentation, highlighting syntax, or ensuring the text output is grammatically correct and coherent. Prerequisites. Upstage account to access and use Chat Upstage. A user needs an account with Upstage, which provides access to the model and its capabilities. Upstage Application Programming Interface Key. The API key is a unique identifier associated with an Upstage account, allowing authorized users to access and interact with the Chat Upstage model through the Upstage Application Programming Interface. Chat Upstage model. Depending on the specific task or desired output, a user might need to choose a specific Chat Upstage model. Upstage may offer different models trained on different datasets or specialized in certain domains. Chat Upstage model name. This refers to the name of the specific model within Upstage that the user selects for generating outputs. For instance, Upstage might offer models named code generation, story writing, or translation. Fine-tune parameters. Model temperature. This parameter controls the creativity and randomness of the generated outputs. A higher temperature leads to more diverse and unexpected results, while a lower temperature produces more predictable and conservative outputs. Max tokens. This parameter sets a limit on the length of the generated output. It helps control the size of the code or text generated by the model, preventing excessively long or verbose outputs. Challenges and fixes. Incorrect output format. Sometimes the generated output might not be formatted according to the user's expectations. The output code might not have the desired indentation, or the text output might not follow the requested style. Use correct output format to address this issue. The user might need to adjust the prompt or provide further instructions to ensure that Chat Upstage generates outputs with the desired format. Model errors. The Chat Upstage model might encounter errors during the processing of a prompt, resulting in unexpected outputs or even failures. These errors can be caused by factors such as ambiguous prompts, model limitations, or technical issues within the Upstage infrastructure. Debug model errors. To resolve these issues, the user might need to rephrase the prompt, try a different model, or contact Upstage support for assistance. Langchain Upstage Chat Models. Chat Upstage Summary. Chat Upstage is a langchain integration for Upstage, a company providing large language model infrastructure and tooling. It allows users to leverage Upstage's capabilities for large language model interactions within langchain. Inputs. The user prompt for the large language model, which is the input text that the model will process and generate a response based on. For example, a prompt could be a question, a request for a story, or a set of instructions. The Upstage large language model to use, which refers to the specific model chosen for the task. Upstage offers various models with different capabilities and training data. Upstage Application Programming Interface Key for authentication. This key acts as a credential to access the Upstage service and ensure secure communication. The Uniform Resource Locator URL of the Upstage Application Programming Interface endpoint. This URL specifies the exact location of the Upstage service that the langchain integration will interact with. Outputs. The generated response from the Upstage large language model, which is the output produced by the model based on the provided prompt and selected model. The response can be a text, code, summary, translation, or any other output format supported by the model. Steps. Initiate the Chat Upstage interaction. Setting up the necessary connections and configuration for the integration. Create a Chat Upstage instance, which is a representation of the integration within the langchain framework. Deliver the prompt to the Chat Upstage instance, making the prompt available for processing by the upstage large language model. Retrieve and return the response generated by the upstage large language model, making the output available to the langchain application. Prerequisites. An upstage account is required, which is an account on the upstage platform providing access to their large language models in services. Obtain an API key and endpoint URL from your upstage account. These credentials are necessary to authenticate and access the upstage service. Upstage Application Programming Interface Key, which is a unique identifier for your upstage account. This key is essential for authentication to ensure secure access to the upstage service. Fine-tune parameters. Temperature, which is a parameter that controls the creativity and randomness of the response generated by the large language model. A higher temperature value results in more diverse and potentially less predictable outputs, while a lower temperature value leads to more consistent and predictable responses. Maximum tokens, which is a parameter that limits the maximum number of tokens in the response generated by the large language model. Tokens are the basic units of text in a large language model, and setting a limit on the maximum number of tokens can help control the length of the output. Challenges and fixes. Authentication issues can arise if the provided application programming interface key or endpoint URL is incorrect or outdated. Ensure the accuracy of the API key and endpoint URL by verifying them. In your upstage account settings, rate limiting occurs when the number of requests to the upstage service exceeds the allowed threshold within a given time frame. Implement appropriate token limits and rate control mechanisms by adjusting the maximum number of tokens in the responses and managing the frequency of requests to the upstage service. Model availability can be a concern if the desired upstage large language model is not accessible or has reached its usage quota. Check the availability and quotas of the desired model in your upstage account to ensure its accessibility and availability for use. Response formatting issues can occur if the generated response does not conform to the expected data structure or formatting. Ensure consistent formatting and data structures by setting clear expectations for the response format and implementing necessary processing steps to ensure compliance. Langchain Upstage Layout Analysis. Upstage Layout Analysis Loader. This component loads a layout analysis model from Upstage. Upstage is a platform that provides pre-trained AI models for various tasks including layout analysis. Inputs. This component takes a document as input. The document could be in various formats, such as PDF, image, or text. Outputs. The component outputs the layout analysis of the input document. This analysis can include information about the document structure, such as the location of text, tables, images, and other elements. Steps. The component first initializes the Upstage Layout Analysis Loader. This step sets up the connection to the Upstage platform and prepares the model for use. Next, the component loads the specified model from Upstage. This model is a pre-trained AI model that specializes in layout analysis. Finally, the component analyzes the input document's layout using the loaded model. This process identifies the different elements in the document, their positions, and their relationships. Prerequisites. An Upstage Application Programming Interface API key is required for accessing the Upstage platform and its models. The API key is a unique identifier that allows the component to authenticate with Upstage. To obtain an API key, users need to sign up for an Upstage account. This is the actual API key that grants access to Upstage services. It is typically a long string of characters and should be kept confidential. The component requires a specific upstage model for performing layout analysis. The model name specifies which pre-trained model to use. Upstage offers various pre-trained models, each optimized for different types of document layouts. This is the name of the upstage model, such as Layout Analysis Model version 1. The user needs to choose the appropriate model for their specific layout analysis needs. Fine-tune parameters. The component allows users to fine-tune the model. This involves adjusting the model's parameters to improve its performance on specific types of documents. Challenges and fixes. This challenge arises if the provided API key is invalid or expired. This could happen if the key was mistyped, the account associated with the key was deactivated, or the key's validity period has expired. To resolve this, ensure that the API key is entered correctly and is still active. If necessary, generate a new API key from the upstage account. This challenge occurs when the specified upstage model is unavailable. This could happen if the model name is misspelled, the model was removed from upstage, or the model is temporarily unavailable. To address this, verify the model name and ensure that it exists on upstage. Double-check that the model is available for use. If the model is unavailable, consider using a different model or contacting upstage support for assistance. Langchain upstage layout analysis. Validate API key summarization. This step describes how to validate an upstage application programming interface key using langchain. This key is a unique identifier that allows access to Upstage's layout analysis services. Inputs. The application programming interface key is a unique identifier that is provided by Upstage to access their services. It is essential for authorization and security purposes. Outputs. The output of the validation process is a status indicating whether the provided application programming interface key is valid. A successful validation will return a positive status, confirming the key's authenticity. Steps. The process begins by sending the application programming interface key to Upstage's servers using a secure communication protocol. This step involves transmitting the key as a request to Upstage's system. Upstage's servers will then process the received application programming interface key and respond with a validation status. This response indicates whether the key is recognized as valid, and it might include additional information or error details. Prerequisites. To perform this validation process, an Upstage account is necessary. This account is a prerequisite because it is associated with the application programming interface keys provided by Upstage. An Upstage application programming interface key is required for authentication. This key is used to identify and authorize the user to access Upstage's services. Fine-tune parameters. No fine-tuning parameters are required for this validation process. The validation process is typically straightforward and does not involve any customization. Challenges and fixes. An invalid application programming interface key might be a common error. This could be due to typos, incorrect key input, or an expired key. To fix this issue, ensure the application programming interface key is entered accurately. This can be done by carefully reviewing the key and comparing it to the original provided by Upstage. Network connectivity issues can prevent successful communication with Upstage's servers. This can be caused by a temporary disruption in the network, a firewall blocking access, or a server outage. To troubleshoot network issues, verify that the internet connection is working properly. Check for any network connectivity problems that might be preventing access to Upstage's services. Confirm that Upstage's servers are operational and accessible. This can be done by checking Upstage's status page or contacting their support team. Langchain Upstage Layout Analysis Get from Param or ENV Summary. This component retrieves information from either provided parameters or environment variables. It acts as a versatile tool for accessing data from various sources, enhancing flexibility and adaptability in workflows. Inputs: the name of the parameter to retrieve, the name of the environment variable to retrieve. Outputs: the extracted value, obtained from either the provided parameter or the environment variable. Steps: the component first checks if a parameter with the specified name is present in the input. Parameters: if the parameter is not provided, the component searches for an environment variable with the specified name. Once a value is found, either from the parameter or the environment variable, the component returns the value. Prerequisites: the component requires either a parameter or an environment variable to be present. The presence of either ensures that the component can successfully retrieve a value. Fine-tune parameters: this component does not require any fine-tuning parameters. Challenges and fixes: if the component is unable to locate the value in either parameters or environment variables, it raises an error. This signifies that the requested information is not available. The component throws an error, indicating that the specified value was not found in either the parameters or environment variables. This error helps to identify missing or incorrect configuration. If the retrieved value is not of the expected data type, the component attempts to convert it to the desired type. The component attempts to convert the retrieved value to the expected data type. If successful, it returns the converted value. If the conversion fails, the component raises an error, signaling a type mismatch between the retrieved value and the expected type. This error helps to identify issues in data formatting and compatibility. Langchain Upstage Layout Analysis Validate File Path Summary. This YAML describes the process of validating the file path for layout analysis. It defines the inputs, outputs, steps, prerequisites, and challenges associated with this validation process. The goal is to ensure that the provided file path is valid and points to an existing file before proceeding with the layout analysis. Inputs: file path. This input represents the file path that needs to be validated. For example, it could be a string like home user documents report.pdf or C users public documents sample.txt. This path will be checked for its validity and the existence of the file it points to. Outputs: Boolean. This output represents the result of the validation process. It will be either true if the file path is valid and the file exists, or false if either the file path is invalid or the file does not exist. This Boolean value will guide the subsequent actions based on the validity of the provided file path. Steps: check if the file path is valid. This step involves verifying the format and structure of a provided file path. It ensures that the path adheres to the operating system's conventions for file paths. For instance, on Windows, the path should include backslashes as separators, while on Unix-based systems, forward slashes are used. This step also checks for the presence of any special characters that are not allowed in file paths. Check if the file exists once the file path is validated. This step verifies the existence of the file at the specified location. It uses system functions to check if the file is present and accessible. This step is crucial to avoid attempting to process a file that doesn't actually exist. Prerequisites: file path. This prerequisite represents the essential input for the validation process. Without a valid file path, the validation cannot proceed. The file path should be provided as a string that correctly points to the location of the file to be analyzed. File. This prerequisite indicates the existence of the file at the specified path. The validation process requires that the file exists and is accessible. If the file does not exist, the validation will fail, and the process will be stopped. Challenges and fixes. File path not valid. This challenge occurs when the provided file path does not conform to the expected format or contains invalid characters. For example, a path with invalid characters like or would be considered invalid. The fix for this challenge is to return false as the output, indicating that the validation process failed due to an invalid file path. File does not exist. This challenge arises when the provided file path points to a location where the file does not exist. For example, the path might be incorrect or the file might have been deleted. The fix for this challenge is to return false as the output, indicating that the file does not exist and the validation process failed. Langchain upstage layout analysis. Validate file path summary. This component validates the file path for layout analysis, ensuring that the specified file exists, is accessible, and conforms to the supported format. Inputs. File path. This is the path to the file containing the document for layout analysis. The path can be a local file system path, a URL, or a cloud storage location. For example, path to document.pdf or https example, com document, docs. Outputs. Boolean. The component outputs a Boolean value indicating whether the file path validation was successful. If the file exists, is readable, and conforms to the supported format, the output is true. Otherwise, it is false. Steps. Check if file path exists. This step verifies if the specified file path points to a real file. It checks for the existence of the file on the file system, cloud storage, or the internet. For example, it checks if a file named document.pdf exists at path to document.pdf. Check if file is readable. This step checks if the file at the specified path can be accessed and read. It verifies that the user has appropriate permissions to read the file, considering potential access restrictions. For example, this check ensures that the file isn't password protected or located in a directory with restricted access. Check if file is supported format. This step validates if the file format is supported by the layout analysis component. It verifies if the file extension matches any of the supported formats like PDF, Docs, JPEG, PNG, etc. For example, it checks if the file extension is .pdf, docs, JPEG, or .png. Prerequisites. Install langchain. This prerequisite ensures that the langchain library is installed. Langchain is a powerful library for building and deploying language models and AI applications. It provides a unified interface for working with different language models, data sources, and tools. It can be installed using the following command: pip install langchain. Install upstage. This prerequisite ensures that the upstage library is installed. Upstage is a library for building and deploying end-to-end AI applications. It provides tools for data preparation, model training, deployment, and monitoring. It can be installed using the following command: pip install upstage. Fine-tune parameters. None. This component does not require any fine-tuning parameters. It operates based on predefined settings and configurations. Challenges and fixes. File path doesn't exist if the file path doesn't point to a valid file. A file not found error will be raised. For example, this error could occur if the file is not found at the specified location, or if the file was deleted. Raise file not found error. The component raises a file not found error to indicate that the specified file path does not lead to an existing file. This exception is typically handled by catching it and providing appropriate error messages or alternative actions. File is not readable if the file exists but cannot be accessed due to permission issues. A permission error will be raised. For example, if the file is located in a directory with restricted access, or if the user lacks the necessary permissions to read the file, this error will occur. Raise permission error. The component raises a permission error to indicate that the specified file cannot be read due to insufficient permissions. This exception is typically handled by catching it and providing appropriate error messages or alternative actions, such as prompting the user for credentials or retrying the operation with different permissions. File is not supported format. If the file format is not supported by the layout analysis component, a value error will be raised. For example, if the component only supports PDF and docs files, but the provided file is in a format like text or zip, this error will occur. Raise value error. The component raises a value error to indicate that the specified file format is not supported for layout analysis. This exception is typically handled by catching it and providing appropriate error messages or alternative actions, such as suggesting alternative file formats or offering conversion options. Summary of langchain upstage layout analysis parsers extracts structured information from documents using layout analysis and parsers. This approach leverages the visual structure of a document to identify and extract key elements, like tables, figures, and text blocks, enabling the system to understand the document's content in a more comprehensive manner. Inputs. Document. The input document can be a PDF, image, or any document format that can be processed by the layout analysis library. For example, a financial report, a research paper, or a legal document. Parser configuration. This defines the specific parameters and settings for the parser, such as the type of parser to use, e.g., table parser, text parser, the target format for the extracted data, and any specific rules or heuristics to apply during parsing. Outputs. Structured data. The output is a structured representation of the information extracted from a document. This can take various forms depending on the parser and the configuration, such as a dictionary, a list of dictionaries, or a tabular data format. For example, extracting key information from a financial report into a table format, or extracting the text content of each section in a research paper into separate dictionary entries. Steps. Layout analysis. This step involves identifying and analyzing the visual structure of the document. This includes tasks like detecting text blocks, tables, figures, and other elements, determining their positions and relationships, and understanding the overall layout of the document. Parser application. Once the layout analysis is complete, the parser is applied to the identified elements to extract the desired information. This step leverages specific algorithms and techniques to interpret the content of each element, such as extracting text from text blocks, converting table data into a structured format, or extracting key information from figures and images. Prerequisites. Layout Analysis Library. This is a software library that provides tools and functions for performing layout analysis on documents. Layout Parser. This library is specifically designed for layout analysis and provides a set of tools for tasks like text detection, block segmentation, and layout understanding. It supports various document formats and offers flexible configurations for different layout analysis scenarios. Paddle OCR. This is an open-source optical character recognition OCR engine that can be used for text recognition in images and documents. It can be used as part of the layout analysis pipeline to extract text from images and convert them into machine-readable text. Parser library. This is a software library that provides tools and functions for parsing specific data structures, such as tables, text blocks, or figures. TabulaP. This library is specifically designed for extracting data from tables in PDF documents. It uses a combination of techniques to detect table structures and extract the data into a structured format, such as a pandas data frame or a CSV file. Camelot. This library provides tools for extracting tables from PDF documents and converting them into various formats. It uses a combination of algorithms and heuristics to identify and extract table data. And it supports a range of output formats, including pandas data frames, CSV files, and Excel spreadsheets. Fine-tune parameters. Parser configuration. This includes parameters like the type of parser, the specific settings for the parser, and any specific rules or heuristics to apply during parsing. Fine-tuning these parameters can significantly improve the accuracy and effectiveness of the layout analysis and parsing process. For example, adjusting thresholds for table detection, specifying specific formatting rules for table cells, or defining rules for extracting text from complex layouts. Challenges and fixes. Handling complex layouts. Some documents have intricate layouts with nested tables, overlapping elements, or unusual formatting. Handling such complex layouts requires advanced layout analysis techniques. Use advanced layout analysis techniques like graph-based layout analysis, deep learning models trained on layout structures, and adaptive thresholding can help in accurately identifying and segmenting complex elements in documents with complex layouts. Parser accuracy. The accuracy of the parser is crucial for extracting the correct information from the document. Factors such as the quality of the document, the complexity of the layout, and the quality of the parser can influence the accuracy of the output. Fine-tune parser parameters. Fine-tuning the parser parameters can significantly improve the accuracy of the extracted data. This includes adjusting thresholds for text recognition, table detection, or other parsing tasks, as well as experimenting with different parsing algorithms and techniques to find the optimal combination for the specific document type and layout. Langchain upstage layout analysis. Parsers get from param or env summary. This parser retrieves configuration settings from either environment variables or provided parameters, making it flexible and adaptable to different deployment scenarios. Inputs. Parameter values. These are configuration values passed directly to the parser as input, allowing for explicit control and customization. For example, an API key or database connection string could be provided as a parameter. Environment variables. Configuration values stored within the system's environment, providing a more general and persistent approach. Environment variables are often used for settings like logging levels or resource paths, which are usually not specific to a particular execution but rather apply globally. Outputs. Configuration values. This is the combined set of configuration values obtained from both parameters and environment variables. It serves as the final set of settings used by the parser for its operations. Steps. Check if the configuration parameter is provided in the parameters this step prioritizes explicitly provided parameters over environment variables, allowing for overrides in specific cases. If not, check the environment variable for the same parameter. This step ensures that the parser can Fallback to environment variables if the specific parameter is not explicitly provided. Prerequisites. Python 3.8. This specifies the minimum required version of the Python programming language for the parser to function correctly. Python 3.8 provides essential features and libraries that are utilized by the parser. Pip install langchain upstage. This command instructs the user to install the necessary Python libraries, langchain and upstage, which are essential for the parser's functionality. These libraries provide tools for natural language processing (NLP), data processing, and other relevant functionalities. Environment variables or parameters with desired configuration values. This requirement states that either environment variables or parameters must be defined to provide the necessary configuration values to the parser. For example, an environment variable could define a database connection string, while a parameter could provide a specific API key for a particular service. Fine-tune parameters. None. This indicates that there are no specific parameters for fine-tuning the parser's behavior or performance. Challenges and fixes. Parameter name conflict. This challenge occurs when a parameter name is identical to an environment variable name, leading to ambiguity. This can be resolved by using unique names for both parameters and environment variables, ensuring clear distinction and avoiding accidental overrides. For instance, using API key as a parameter name and API key as an environment variable name would prevent this conflict. Missing configuration value. This challenge arises when a required configuration value is not provided in either parameters or environment variables. This can be resolved by ensuring that the required configuration values are set appropriately. For example, if an API key is required, it should be either provided as a parameter or defined as an environment variable. Type mismatch between environment variable and parameter. This challenge occurs when the data type of a value obtained from an environment variable does not match the expected data type for the corresponding parameter. This can be resolved by ensuring that the data types are consistent between parameters and environment variables. For instance, if an API key is expected as a string, both the parameter and environment variable should be defined as string values. This consistency ensures that the parser can correctly interpret and process the configuration values. Langchain upstage layout analysis. Parser's upstage layout analysis. Parser summary. This description explains the upstage layout analysis parser, a tool used to analyze the layout of a document. It leverages upstage, a powerful library for working with document layouts. The parser extracts structured data from the document based on its layout. Inputs. The input for this parser is a document. This can be a PDF file, an image file, or any other file format supported by Upstage. Outputs. The output of this parser is structured data. This data represents the layout of the document, including information about the positions of text, images, tables, and other elements within the document. Steps. The parser starts by loading the document. This step involves reading the document data and preparing it for layout analysis. Next, the parser extracts layout information from the document using Upstage. Upstage analyzes the document structure and identifies the different elements within it, such as text blocks, images, and tables. Finally, the parser converts the extracted layout information into structured data. This structured data can be used for various tasks, such as document summarization, document search, and document classification. Prerequisites. The Upstage layout analysis parser requires the installation of Upstage. This can be done using the pip package manager pip install Upstage. The document input should be in a format supported by Upstage. This typically includes formats like PDF and images. Fine-tune parameters. The Upstage layout analysis parser uses model parameters to control the behavior of its layout. Analysis algorithms. These parameters can be fine-tuned to optimize the parser's performance for specific types of documents or use cases. Challenges and fixes. One potential challenge is missing layout information. This can occur when the document is poorly formatted or has missing data. In this case, it might be necessary to use a different layout analysis model that is better suited to handle such scenarios. Another challenge is incorrect layout information. This can happen if the layout analysis model makes mistakes in identifying the elements within a document. To address this, one can fine-tune the layout analysis model to improve its accuracy on specific types of documents. Langchain Upstage layout analysis parsers validate file path summary. This component validates a given file path to ensure it is a valid file path and points to an existing and accessible file on the system. Inputs. File path. This input represents the string value of the file path that needs to be validated. For instance, it could be home user documents report.pdf or C users documents report, docs. Outputs. True or false. The output of this component is a Boolean value indicating whether the provided file path is valid. If the file exists and is accessible, the output will be true. If the file does not exist or is inaccessible, the output will be false. Steps. Check file existence. This step checks whether a file exists at the specified file path. It verifies whether the file exists in the file system by checking the corresponding directory. Structure. A common approach is to use the OS path exists function in Python. Check file accessibility. This step verifies whether the user has the necessary permissions to access the file at the provided file path. This step checks if the user has read permissions to access the file. In Python, the OS access function is commonly used to check file permissions. Prerequisites. Python installed to execute this component. Python programming language must be installed on the system. This can be done through the official Python website or using a package manager like apt on Linux or Homebrew on Mac OS. Pip install langchain upstage. This step installs the langchain upstage Python package which provides the necessary functionalities for this component. It's a prerequisite for using the component. You can install it using the pip package installer in your terminal. Layout analysis parser installed. This component relies on a layout analysis parser for understanding the structure of documents. A commonly used library for this purpose is called layout analysis parsers. This step installs the layout analysis parser's Python package which allows the component to analyze the layout of documents. Fine-tune parameters. None. This component does not require any specific fine-tuning parameters. It operates based on the default configuration and does not need any additional parameters to be customized for its operation. Challenges and fixes. File not found. If the file specified by the file path doesn't exist on the system, a file not found error might occur. This can happen due to an incorrect file path, the file being deleted, or the file not being present in the specified location. Handle file not found error. To handle this scenario, you would typically catch the file not found error exception. This would involve handling the situation gracefully, perhaps by providing feedback to the user, logging the error, or performing alternative actions depending on the application's logic. File not accessible. If the file exists but the user does not have the necessary permissions to access it, a permission error might occur. This could happen if the file is set to read-only, or the user lacks the required permissions to access the specific folder. Handle permission error. To handle this scenario, you would typically catch the permission error exception. This might involve informing the user about the lack of permissions, prompting them to provide credentials or change permissions, or taking other appropriate actions based on the application's context. Langchain upstage layout analysis parsers validate file path summary. This component validates the file path for layout analysis parsers. It ensures that the provided file path is valid, the file exists, is readable, and is in a supported format. Inputs. File path. This is the path to the file that will be processed by the layout analysis parser. For example, it could be path to file.pdf or C users documents file, docs. Outputs. Boolean value indicating whether the file path is valid. This output is a Boolean value. True if the file path is valid and false otherwise. Steps. 1. Check if file exists. This step checks if the file at the provided path exists. 2. Check if file is readable. This step checks if the file at the provided path is readable. 3. Check if file is of supported format. This step checks if the file is in a supported format for layout analysis. For example, supported formats could be PDF, docs, or images. Prerequisites. File path should be valid. The file path provided as input should be a valid path to a file on pay system. For example, path to file.pdf is a valid file path. File should exist. The file at the provided path should actually exist on the system. This ensures that the parser is not attempting to process a non-existent file. File should be readable. The file at the provided path should be readable by the parser. This ensures that the parser has the necessary permissions to access the file and its contents. File should be in supported format. The file at the provided path should be in a format that is supported by the layout analysis parser. For example, the parser may only support PDF and docs files. Fine-tune parameters. None. This component does not have any fine-tune parameters. This means that its behavior cannot be adjusted by the user through any configuration settings. Challenges and fixes. File does not exist. If the file does not exist at the provided path, a file not found error will be raised. This indicates that the file could not be found. File is not readable. If the file exists but is not readable, a permission error will be raised. This indicates that the parser does not have the necessary permissions to access the file. File is not in supported format. If the file is not in a supported format for layout analysis, a value error will be raised. This indicates that the parser cannot process the file because of its format. Langchain upstage tools. Groundedness check. Groundedness check. Description of summary. Groundedness check verifies whether the generated text is supported by the source documents. This tool analyzes the generated text to determine if the claims made within it can be backed up by information present in the provided source documents. This ensures the credibility and accuracy of the generated content, especially when working with large language models that may sometimes generate factually inaccurate or unsupported statements. Description of inputs. This refers to the text that has been generated, typically by a large language model, which will be evaluated for groundedness. For instance, if a model has been prompted to write a summary of a scientific paper, the generated summary would be the input text. These are the source documents used as the basis for generating the text. These documents could be articles, websites, books, or any other type of information source. It's important to note that the source documents are essential for assessing the groundedness of generated text. Description of outputs. This represents a numerical value between 0 and 1, indicating the level of groundedness of the generated text. A score of 1 signifies that all claims in the generated text are supported by the source documents, while a score of 0 suggests no claims are supported. The score is calculated based on the ratio of supported claims to the total number of claims in the generated text. This output provides a list of claims found within the generated text that are not supported by the source documents. These unsupported claims are flagged as potential inaccuracies or fabrications. This list is crucial for identifying and rectifying any factual errors in the generated content. Description of steps. This step involves extracting claims from the generated text. A claim is a statement that asserts a specific fact or opinion. The tool uses natural language processing techniques to identify these claims, which could be expressed as assertions, propositions, or even implicit statements. This step aims to identify supporting evidence for each extracted claim from the source documents. This involves matching claims to relevant information within the source documents. This matching can be based on keyword matching, semantic similarity, or other advanced techniques. The goal is to establish a connection between the claims and the information contained within the source documents. This step involves calculating the groundedness score based on the ratio of supported claims to the total number of claims. A higher ratio implies a higher groundedness score. For instance, if 10 claims are extracted from the generated text and 8 of them are supported by evidence, the groundedness score would be 0.8. This step returns the list of unsupported claims to the user. These claims are presented as potential errors or inaccuracies in the generated text. The list provides valuable feedback for revising the generated content to improve its accuracy and reliability. Description of prerequisites. These are the necessary source materials required to run the groundedness check tool. The source documents should be in a format that can be processed by the tool. This could include plain text files, PDFs, URLs, or other formats that can be converted to text. The tool needs access to these documents to assess the groundedness of the generated text. This refers to a text generation model, which is a machine learning model capable of generating human-like text. Examples include GPT-3, Llama, and similar models. The generated text, which will be evaluated for groundedness, is produced by this text generation model. Description of fine-tune parameters. This refers to the method used to extract claims from the generated text. There are various techniques available, each with its strengths and weaknesses. The choice of method depends on the specific needs of the application and the complexity of the generated text. For example, some methods might focus on identifying explicit statements while others might also try to extract implicit claims. This parameter specifies the algorithm used to match claims in the generated text to supporting evidence in the source documents. Different algorithms employ different strategies for matching claims and evidence, such as keyword matching, semantic similarity, or pattern recognition. The choice of algorithm can significantly influence the accuracy and efficiency of the groundedness check. Description of challenges and fixes. Identifying complex claims, such as those that are implicitly stated or require deep understanding of the context, can be challenging. Advanced claim extraction techniques, like dependency parsing or semantic role labeling, can be used to better capture complex claims. These techniques can analyze the structure and meaning of sentences to identify more nuanced claims that may not be readily apparent through simple keyword matching. Matching evidence across different formats, like text, PDF, and URLs, can be difficult due to the variations in structure and content representation. Robust evidence matching algorithms are needed to handle these differences. These algorithms should be capable of extracting relevant information from various formats and comparing it against claims in the generated text. This might involve using techniques like document similarity measures or semantic analysis to bridge the gap between different formats. Handling ambiguous claims, which can have multiple interpretations, can be challenging because the same claim might be supported by different pieces of evidence. Depending on the interpretation, disambiguation techniques are required to resolve such ambiguities. These techniques might involve analyzing the surrounding context of the claim, identifying the intended meaning based on the overall text, or employing knowledge bases to resolve the ambiguity based on external information. Evaluating groundedness score effectively requires considering various factors and using multiple metrics. A single metric might not provide a comprehensive picture of groundedness. Using multiple metrics and considering context is crucial. For example, in addition to the ratio of supported claims, the tool might consider the complexity of the claims, the quality of the supporting evidence, and the overall coherence of the generated text to provide a more nuanced assessment of groundedness. Langchain Upstage Tools Groundedness Check. Upstage Groundedness Check. This tool assesses the groundedness of a response generated by a language model in relation to the provided context. Groundedness refers to the extent to which the response is supported by the provided context, ensuring it doesn't fabricate information or hallucinate. Inputs: the text output by the language model. The context provided to the language model. This context could be a document, a set of instructions, or any other relevant information. Outputs: a numerical score reflecting the groundedness of the response. A higher score indicates stronger grounding, signifying that the response aligns well with the provided context. A detailed explanation accompanying the groundedness score. This explanation elaborates on the factors contributing to the assigned score, highlighting specific instances where the response aligns or diverges from the context. Steps: the response and context are broken down into individual units called tokens. These tokens are typically words or punctuation marks, representing the fundamental building blocks of the text. A similarity score is calculated between the tokenized response and the tokenized context. This score quantifies the extent to which the response aligns with the provided context on a lexical level. The calculated similarity score is mapped to a groundedness score, effectively translating the raw similarity value into a more human interpretable measure of grounding. This mapping can be adjusted to reflect the specific requirements and desired interpretation of a groundedness score. A clear and concise explanation for the assigned groundedness score is generated. This explanation articulates the key factors contributing to the score, including specific examples from the response and context that justify the chosen score. Prerequisites: an upstage language model is required to utilize this tool. Upstage models are designed to generate human-like text, and they leverage a wide range of parameters and techniques to achieve high-quality outputs. The tool leverages the capabilities of the upstage model to assess the groundedness of generated responses. Fine-tune parameters. The similarity threshold represents a cutoff point for determining whether the response aligns sufficiently with the context. If the similarity score falls below the threshold, the response might be considered poorly grounded. The threshold can be adjusted based on the specific needs and tolerance for deviations from the context. The groundedness score mapping defines the relationship between the similarity score and the final groundedness score. This mapping allows for fine-tuning the interpretation of the similarity score, enabling it to align more closely with the desired level of groundedness assessment. For instance, a mapping could assign higher groundedness scores to responses that exhibit a high level of similarity to the context, while assigning lower scores to responses that deviate significantly from the context. Challenges and fixes. There could be mismatches between the context and response due to factors like inconsistencies in wording, different interpretations of the same information, or missing information in the context. This can lead to a low similarity score, indicating poor grounding. The similarity threshold can be adjusted to accommodate such mismatches. Lowering the threshold would make it easier for responses to achieve a high groundedness score, allowing for more flexibility in handling minor deviations from the context. Responses might be ambiguous or unclear, leading to difficulties in establishing a clear connection between the response and the provided context. This ambiguity can hinder the accurate assessment of groundedness. Providing additional context can help to alleviate ambiguity, leading to more precise and reliable groundedness assessments. Supplying more information about the topic, the desired response style, or any other relevant details can enhance the clarity of the response and facilitate a more accurate evaluation of its groundedness. Upstage groundedness check tool description. This tool checks if the generated text is grounded in the input context. It compares the generated text to the source context to determine if the generated text is supported by the source context. Inputs. Input text to check for groundedness. This is the text generated by a language model. The source context used to generate the input text. This is the text used by the language model to generate the text. For example, if the language model is asked to summarize a news article, the news article would be the source context. Outputs. Whether the input text is grounded in the context. This is a Boolean value indicating whether the generated text is grounded in the source context. For example, if the generated text is a summary of the source context, this would be true. Explanation for the groundedness check result. This provides the rationale for the groundedness check result. For example, if the generated text is grounded in the source context, this might provide the specific sentences from the source context that support the generated text. Steps. 1. Tokenize the input text and source context. This step breaks down the generated text and source context into individual words or phrases tokens. 2. Compute the similarity between the input text and source context. This step calculates how similar the generated text is to the source context. This can be done using different similarity metrics, such as cosine similarity or Jaccard similarity. 3. Determine the groundedness based on the similarity score. This step compares the similarity score to a predefined threshold to determine if the generated text is grounded in the source context. A higher similarity score indicates a greater degree of groundedness. Prerequisites. Input text and source context. The input text should be a string, and the source context should be a list of strings or a single string. This ensures that the tool has the necessary information to perform the groundedness check. Similarity metric. This is a method for calculating the similarity between the generated text and the source context. Some common similarity metrics include cosine similarity, Jaccard similarity, and Euclidean distance. The choice of metric can affect the groundedness check result. Fine-tune parameters. Similarity threshold. This is a threshold value used to determine if the generated text is grounded in the source context. A higher threshold requires a higher degree of similarity between the generated text and the source context for the generated text to be considered grounded. Tokenization method. This is the method used to break down the generated text and source context into individual words or phrases. Different tokenization methods can lead to different interpretations of the text, which can affect the groundedness check result. Challenges and fixes. Low similarity score between input text and source context. This issue can occur if the generated text is not closely related to the source context. To address this, the similarity threshold can be increased. Inconsistent tokenization. This issue can occur if different tokenization methods are used for the generated text and the source context. To address this, a more robust tokenization method can be used that is consistent across both inputs.